Welcome to Paris question number 149. In this podcast, we'll be looking into a new cool idea for aerodynamics, which is a flying train. So there are a couple of things to cover here. The first is, isn't a flying train just an airplane? And secondly, what is the point? So both of these questions can really be answered by looking at the draw card of this flying train, and that is, it utilizes ground effect to increase its efficiency dramatically. And we've done another podcast on ground effect, which you can look into as well. So in a sense, yes, a flying train is an airplane, but the geometry is more like a train with some wings strapped onto it, as you can see here in figure 1. And if you're just listening to this on Spotify, or Google Play or whatever, you can look at the video on Spotify and or our YouTube channel, and you can find some other goodies on our YouTube channel as well. So because this device leans heavily on the ground effect, the main benefits of this over an airplane is efficiency, as we'll cover later on. So passenger airplanes, they cruise well out of ground effect. Their lift to drag ratios, as we will see, are usually a little lower than what these researchers have found for this flying train. And so they're usually around maybe like 8 to 10. So I should also mention that these flying trains operate very close to the ground in order to maximize this ground effect. In this particular paper, the train is like 30 millimeters away from the ground. So this paper is called Influence of Wing Angle of Attack and Relative Position of the Aerodynamics of an Aerotrain. So let's see what they found out. And I should also mention that this Aerotrain is what they call the flying train. So in figure 1, there are a couple concepts for this flying train idea. And the first one, the top part here, is simply a train with some wings strapped onto it. But the other one is similar, but the wings are not typical planar wings. So you can see here, this bottom one, these wings go in this like kind of loop sort of fashion. So in other words, these wings are not flat, but closed shapes that start and end at the train. The benefit of these types of wings, which are called non-planar, is that the induced drag drops. So why does this happen? So to illustrate why, let me draw in paint here. We have a wing. Let's say we have, I should get the drawing pencil. We have a wing here, and we have like the wing root there. Then we have on top, we know that we have from other podcasts, high pressure underneath, and we have low pressure on top. So for all fluids, including air, the natural progression is that the fluid moves from high pressure, so over here, to low pressure up here. And in this instance, the bottom surface is the low pressure and the top surface is the high pressure. So this results in a vortex forming, and that is wasted energy. This is drag, and more accurately, lift-induced drag. So this term lift-induced drag comes about because the drag arises from the wing-producing lift. Lift is produced because we have differences in pressure between the bottom and top surface. We have high pressure underneath, low pressure on top. There's a pressure difference that results in a net force up, this way. So hence the name lift-induced drag. But this vortex can only happen if the wing has a wingtip. So we have here the wing tip here, and it's finite. If the wing is a closed shape, so let's say we have the same wall, but then we have the wing coming out, and then it goes up and then back around, as we saw in figure 1b here. There is no way for the flow to actually come here and come in. So that means that we can't really get this wingtip vortex forming, hence the induced drag drops. Now notice that I said the induced drag drops. It doesn't disappear completely, and that is because there is still mixing of the high and low pressure regions, and that still results in some induced drag forming. You can't really get rid of that entirely, like if you go into the wake, for example, that will still happen to some extent. So, with this second concept, flying train, or as they call it, the Aerotrain, the closed wings result in a higher efficiency. So one difficulty that the authors point out about these flying trains is that it accelerates and decelerates between stations, and the velocity obviously changes then. We all know that the amount of lift produced is proportional to the velocity squared, so a doubling of the velocity results in 4 times the amount of lift. That increased lift raises the train further from the ground, and not only affects the ground effect, but also potentially the stability of the train as well as the ride comfort, because gusts can result in the train jumping up and down and shaking people about inside. So that's not a great thing. As such, the train's wings need to be equipped with flaps to control the angles of attack and keep the train flying at a constant height above the ground during its operation. When the flying train is stationary, it obviously is not producing any lift, so to get the train started, the undercarriage wheels then need to take the load until the train has accelerated to the point where it produces sufficient lift to lift off the ground, and then it can start flying around. So one major difficulty of this flying train concept is that the front wings will see a very different flow to the rear wings. So we see here in this particular figure, we have 3 sets of wings. Let's just say we have the front wings and the rear wings. Still, they will see very different flows, as will this middle wing as well. So as such, perhaps the same design for the front and rear wings are not a good idea. Perhaps, depending on the flow conditions each of these wings sees, they should have different wing geometries and different configurations. These are all considerations that need to be considered, and the authors are looking into some of them. So let's move on to their investigation. First of all, they used their experimental setup. It's quite impressive that these researchers went with this experimental approach, because it seems like most researchers these days go with CFD mainly because of how much easier it is to set up. With this experiment, you literally need to make a contraption that approximates a flying train, not an easy thing to do. So I do like these researchers. They remind me of a younger me, not too much younger though, maybe even a little older. But with this model, they chose a 1 to 10 scale. The entire length of the train is 1 meter. The airfoil profile chosen is an LA203A. They said that they selected this airfoil because it has excellent aerodynamic performance. The airfoil, the LA203A, is highly cambered at 5.5 degrees of the chord, 5.5% of the chord, and quite thick at 15.7% thickness to chord ratio. It is kind of reflex at its trailing edge, and in terms of its performance, I would have to agree with the authors and say that it is excellent. I mean, it has lift coefficients up to 1.7 and a very gradual stall pattern. The stall pattern is very impressive. For example, it sees a maximum lift coefficient of 1.7 at about 10-degree angle of attack, and then it just plateaus to about 17 degrees. The lift coefficient is still around 1.6 at this point, so it just like flattens off and it doesn't really die off, or it doesn't really even jump down. So as for the lift to drag ratio, this airfoil produces a maximum of 160 at a 5-degree angle of attack. Nice. Another thing that these researchers looked at were the relative positions of the front and rear wings. So we see here we have the front wings and the rear wings on the train, and in this figure here we see some different configurations. So there are 4 different ones. The first and third setups, so this one and this one, are where the front wings are 2.75 chords ahead of the rear wings. The difference between the front and third setups is that the front wings for the first setup is located much closer to the front of the train than for the third setup. So the third setups, the wings are kind of staggered. For the second setup, the front and rear wings are 3 chords apart. So this is the maximum difference between the two. And for the fourth setup, the front and rear wings are 2.5 chords apart. In figure 5, we see that the train hovers 30 millimeters from the ground, and there is a 30 millimeter clearance between the walls and the wing tips. Also, for this particular flying train, the wings have winglets, which means that these wings are not actually planar, they are non-planar. The wind speed for these tests was 35 meters per second, and the pressure distributions over the wings are given in figures 10 to 13 for the 2 most extreme wing setups, where the airfoils were 3 chords apart and 2.5 chords apart. So on these figures, let me go down to this one. We have figure 10, figure 11, 12, and 13. So on these figures, we can see that the locations of 1, 2, 3, and 4 are seen in the legend. So we have like these diamond, square, triangle, and circle. And these locations refer to where along the airfoils these pressure distributions are found. So figure 8 shows the location 1 is just near the wing root, so they sliced through here. Figure 4 is just near the winglet, where they slice through here. Vice versa. And then figure location 2 and 3 are between these 2 locations. So overall, for all the different wing locations, the front and rear wings, the bottom pressure doesn't really change across the airfoil. So we can see that these lines are always quite close to each other, regardless of whether you're near the wing root or the wing tip. The same goes for this one, and then for the rear wings as well, the same kind of thing occurs. There is some deviation, but generally speaking, they are quite similar. So what I mean by that is that regardless of whether the wings are close together or not, and also whether they're close together or not, the pressure distributions on the underface don't really change too much. The same can largely be said for the upper surface as well. We do see some differences along the airfoil span though, so you can see here that there is some deviation once we get to the maximum or the minimum pressure coefficient. When we are close to the wing root, the airfoil's top surface experiences an even lower pressure, which means that the wing section near the root is producing more lift than near the wing tip, which is to be expected even with winglets, because winglets don't completely neutralize the airflow bleeding. Figure 14 shows the streamlines slicing through the front and rear wings. So let's go down to that. As expected, the air that flows over the top of the front wing is the air that hits the rear wing. This is expected because the front wing is producing lift, so we know that the wake will then subsequently be angled down. However, above the wing we also see angled flow downwards as well. So when we go downstream a little, that air that was angled down is now in line with the rear wing, and that's what's hitting this rear wing, these light grey lines. With this, what this also means is that the effective angle of attack of the rear wing will also drop because the oncoming flow is angled down now. That means that the flow is more in line with the pitched up wing, thereby reducing the difference in angle between the wing's chord line and the airfoil's direction. So we can see here, like if you were to draw a line between the trailing edge and the leading edge, that line is much more in line with the flow than if the flow was more horizontal. So that upstream wing definitely affects the downstream wing then. So that reduction in the effective angle of attack also reduces the lift produced by the rear wings. That could cause an imbalance in the flying train. So we have like maybe more lift being produced at the front than the rear, or if you have different airfoils at the back, then that could change it again. So the rear wing's flap should change to account for this difference to keep the train more level. So let's move on to figure 17 now, where we see the drag, lift, and lift to drag ratio of the train with these different wing positions and angles of attack. So the amount of lift and drag produced here, so these top two figures, are kind of irrelevant because they're not non-dimensionalized. They're not giving the lift or drag coefficients, they're only giving the lift and drag in force, newtons. So hence their values are somewhat arbitrary. I mean, they just really depend on the size of the train or the velocity even. Whereas if we had the lift and drag coefficients, that would be much more robust and we could actually look at them more. So we're not going to look into the lift and drag forces too much, but the lift to drag ratio is very interesting and important because now we are kind of getting rid of that that reliance on just the flow conditions and looking at the non-dimensionalized effect effectively. So we see that lift to drag ratio ranges from 5 to about 12.5. This is about the same as an airplane, but one thing of interest is that the maximum lift to drag ratio occurs at a relatively high angle of attack of 10 degrees, and even more than that. So we can see when we have this 10 degree, like very dark gray section, the lift to drag ratio is quite high still. So for airplanes, this angle of attack isn't usually the most effective. In fact, airplanes are typically designed to give the best efficiency during the greatest phase of flight, which is cruise. They're cruising for like 98% of the time of flight. So we want to maximize the efficiency during this time because that's when we're using the most fuel. So this happens at much lower angles of attack, like 3 degrees perhaps. So to get such a high lift to drag ratio at such a high angle of attack is a little unusual. So overall, the lift to drag ratio was insensitive to the distance between the front and rear wings, as well as how close the front wings was to the train's nose. We can see these different configurations down on this axis here. The lift to drag ratio doesn't really change too much. It might be like 5% in total, but not very much considering how different these locations were. So in addition to these forces, the authors also did some oil flow vids to see where the flow was going. We can see in figures 20, 21, 22, and 23. So I'm going to look at this one here, this figure here, because it's largely indicative of the other figures as well. So one thing that really pops out is that regardless of whether the wing was at the front or rear, there is deflection of the flow near the wing tip and near the wing root. So we can see here, like the streamlines come in and then they blow out towards the center of the airfoil. And also at the wing root, we also get the same thing where they blow out here. So the authors explained the wingtip deflection to be because of the vortex rolling up and that the wingtip vortex still occurred despite the winglets, because the winglets weren't that big. They weren't big enough to completely mitigate this vortex. To some extent, I can understand what they mean, especially because the pattern we see here in the oil flow viz is exactly what you see when you have a wingtip vortex. So if you have a regular wing without this plate here, you will get this exact same kind of thing happening. However, I don't quite understand that this is the same general phenomenon that occurs near the wing roots. So we do get the same phenomenon effectively here. I also think that this phenomenon near the wing root is due to a vortex, but because we're not near the wing root, but because we're near the wing root, not the wing tip, it obviously isn't a wingtip vortex that's causing this. Instead, I think it forms at the junction between the wing's top surface and the train's side. This makes sense because the same thing happens on turbines and compressors where you have the blade meeting a wall. The differences in velocities, not to mention the boundary layers, result in vortices being produced. So perhaps the pattern near the wingtip that the authors attributed to the wingtip vortex is actually because of the the wing top surface meeting the winglet, producing a vortex as well. So I don't know if it really is because there is a wingtip vortex, or whether it's because the vortex is forming because of the top surface meeting this other surface. But it's quite interesting. So from this podcast, we've found that this train is quite insensitive where these wings are, like the lift drag ratio and even the lift and drag produced are quite similar. We also found that the front wing significantly affects the rear wing's aerodynamics, and we need to account for that by changing the wing flap or even changing the airfoil profile. We can see here this is the LA203A airfoil, which had very good aerodynamic performance. So with that, my little analysis, we come to the end of this podcast. So if you liked it, give it a like. If you want to see more like this, click the subscribe button or the follow button, whichever platform you're on. And if you want to get better at aerodynamic theory or CFD, check out our courses in link in the description. And if you want to make your experiments 2% accurate, so they did experiments here, get yourself an atmosphere hawk. And the reason why this is important is because it's an instrument that we make to accurately measure the density of air. The reason why this is important is because the density of air always changes. For example, if you come into your wind tunnel in the morning, then come back after lunch, the density of air has changed by a few percent in just a few hours. The density of air is affected by the temperature, barometric pressure, and humidity. So having even you in the wind tunnel changes the density of air because you're pumping out heat and more water as you breathe and sweat. Just because I'm sure you're working hard in the wind tunnel. What's more, the density of air changes even more than 2 to 4% between days, weeks, months, and seasons. 10-15% changes are very normal, which means that you need to take them into account in your experiments. I'm not sure if the researchers did that. If they didn't, then they would have a 2 to 4% error at least in their results. So what's more, if you don't take them into account, then you're not only are most of the things you're finding in your experiments just random error, because these days when we do experiments, we're really looking for like 2%, 3% changes. It's quite rare to be finding bigger changes than that. But also, when we are trying to use our experimental data to validate our CFD, it won't work, because the one major reason why people have such major problems is not that the CFD is wrong, it's that the density of air that they use in their CFD is not the same as the density of air they're using in their experiments that they're using to validate the CFD. So of course they're not going to line up. So get yourself an atmosphere hawk and make your experiments and CFD more accurate. You can find it in the link in the description. And I'll see you in the podcast. Peace, amigos.